Before start today's class, I believe everyone knows. I posted the first assignment. There's a homework assignment on the Blackboard, so you can find the homework questions here. So can you see? I think so. Okay. So and I'm posting lecture videos, lecture notes, and the lecture videos on the this resources tab on Piazza. So you can find the uploaded lecture notes here, the PDF files, and then some lecture videos, the links. So these are links for lecture videos. Okay, I'm posting lecture videos on YouTube. Also, I uploaded several resources regarding RISC-V ISA. So you can find the RISC-V green card, that is the summary of RISC-V instructions. So you can find this green card on the first page of your textbook. Okay, and also I uploaded the RISC-V instruction set manual. So this is a ISA manual. It's like some normal ISA manual of ARM ISA or x86 ISA. But you can find that this RISC-V ISA is much simpler than other commercial ISAs. Okay, so if you are interested, you can download this RISC-V instruction set manual, and then you can read the part of manuals and then see what is written inside of the ISA manual. Okay, so you can find the reference card here. So it's also a summary of the RISC-V instructions. Okay, so I will also upload the several resources here, so you can please check regularly these resources or some lecture notes, and then post the lecture videos here. Okay. 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 So in the previous class, we learned about the operands of the computer instructions. So I think you can easily understand some operands of instruction. These are very similar to the operands of our normal operators. Okay, so these operands mean data used by operators or instructions. Okay, and then RISC-V instructions have regular forms. So if you see the RISC-V reference card, it's called green card, then you can find several formats here, like R format, I format, other formats. So these instructions have regular formats. So there are several formats, like maybe, I think there are 5 normally used formats in the RISC-V ISA. So if we know the format of the instruction, then we can easily translate this assembly instruction into machine code instructions. Okay. We learned about the operands of the computer instructions. Also, the important topic we learned in the previous class is registers. So you need to remember what registers are inside of a computer processor. So register is very important. It's a very small memory space that stores the data temporarily. So temporarily means that actually we declare our data like actually variable in a high level language, like a equal 1, then this data is assigned in main memory and stored in main memory also, to the assigned space. And then in order to compute using this data, like with some instructions, so we learned about the arithmetic instructions in the previous class. So in order to compute this data is moved to the registers inside of processor, because the register is a very small memory space, so register is very fast. So you may think, oh, so main memory is slow. Yeah, compared to the register file, the speed of the memory, that means the main memory is very, very slow. So we think that, oh, DRAM speed is very high. So yeah, DRAM is very fast. But that's right. Compared to other storage devices such as hard disk drive or SSD, the DRAM is very fast. But compared to register file, the DRAM is very, very slow. So we assume that computer processor execute instruction or single instruction per cycle. So that means the one instruction is executed per cycle. But if the memory is too slow, it's not possible. So in order to solve this issues or problem, and we first transfer the data inside of the main memory into registers. So very fast, because it's very fast. And then the computer execute the instructions that make use of these data stored in register file. So that's why RISC-V instructions, usually arithmetic instructions, accesses registers. So we learned that there are 32 general purpose registers inside of RISC-V processor. So this number of general purpose registers is defined in instruction set architecture manual. So if you read the instruction set architecture manual, then you can find, oh, the number of general purpose register is 32, because it's IV64I. If there are only 16 registers, that means IV32E. Okay, so it's different. So but the RISC-V usually have 32 general purpose registers. Okay, and then this number of registers is defined in instruction set architecture manual. So, and then, so we learned that each register has its own purpose, and but these are just a recommendation. So if we build, when we build a compiler, the compiler engineers just follows these rules defined by also instruction set architecture manual. Okay, so in the previous example, so we assume that the instructions, the computer instructions, directly access the variables, but actually, so in reality, the computer instructions, like the RISC-V instructions, accesses registers. So that means that the data stored in registers are computed by these instructions, and then the result is also, so this is the destination of the instruction. So the result is also stored in one of the registers. Okay. So you should understand this rule. Okay. And then in the today's class, we will learn about memory instructions. So in the previous class, we covered arithmetic instructions. So arithmetic means that it's the plus, add, subtract, multiply, and divide. And then what is the memory instructions? So actually the title of this slide is memory operands. Okay, because memory instructions access data in the main memory. So that is the memory operands. Okay. Let's start from the high level language like C. So A equal 1. So we declared a variable in the C. So it's A equal 1. So that means that I already explained the memory space of this variable A is assigned in main memory. So it's a MM means main memory. So actually it's DRAM in the computer systems. So this memory space is assigned in the main memory, like A. This is the memory space. And then if a space is assigned, that means the address of this variable A is also assigned. So each memory space has its own address, like the house number in apartments or condos. So each house inside of apartment or condos has house number, right? So like this house number, each data space assigned in the main memory has its own address. So the address is also assigned, and then in the assigned space, memory space, this space for variable A is assigned in the main memory. And this data is stored in this memory space for variable A. But I already mentioned that, this is not directly accessed by arithmetic instructions we learned in the previous class. Okay, as usually the normal instructions of RISC-V cannot directly access this data inside of main memory. Then how can we access this data? So if we declare the variable and then this data is stored in the main memory, firstly, then how can we access? So this data stored in the main memory, someone asked the question, okay? So this data firstly stored in the main memory should be transferred to register. It's a register. So we frequently use REG for registers. And then for this data transfers, we use memory instructions, okay? So this is the register file. And then this is main memory. It's a very large, actually. And then A is here. And then in A equal 1. So in order to use this data, this data should be transferred to the register file. So for this data transfer, we use load instruction. Okay, it's a load. Okay. So load instruction is used to transfer data from main memory to register file. And then the other direction should be also supported by RISC-V processors, because if data is calculated, then this data should be also transferred to the main memory, okay? Because A equal 1, B equal 2, and C equal A plus B. Then we calculate the C from data A and B, and then this C is also updated in the main memory. But if we use only arithmetic instructions, actually this result of this computation is stored in the register file. Okay, because I mentioned that other normal instructions cannot access main memory. Only memory instructions are able to access data inside of main memory. Okay, so but in our program, our program also defined the C equal A plus B. So that means the C is assigned in the main memory also, and then C will need to have the result of A plus B. So that means the result of a computation should be updated in the main memory. So for this data, so data transfers from register file to main memory is also required. So this instruction is called the store. Okay, it's store instruction. It's store. So load means that data moves from main memory to, oh, I cannot see my hand. Main memory to register file. And then the store instruction means that the data move from register file to main memory. Okay. There are only two kinds of memory instructions in the RISC-V. Okay. Load and store instructions. Okay. Also, in this slide, you can find the main memory used for composite data. That means that all kinds of data is stored in the main memory, like arrays, structures, and dynamic data. So that means the A equals some variable, say equals some numbers, or P equals some numbers. That means the dynamic data. Also the dynamically allocated arrays are the dynamic data. Okay, so it means that all kinds of data is stored in the main memory, the arrays, structures, dynamic data. And then we use two kinds of memory instructions, load and store, I already explained. And then it's very important. The memory is byte addressed. So what does that mean? I explained that if a variable is assigned in the memory space and each memory space has its own address. Okay. So, but this address is assigned to the some data chunks or some data types. Okay. So for example, if there are like 100 지금 6 square meter houses in the apartment or condos, then and then the room number 1, 2, 3 is assigned to the each house. Okay, then what is the size of this room number? Actually, the size of the unit house. The size of a unit house is 100 square meter. Okay, and it's same to the address. Address is just a room number. It's like a room number for house inside of in the apartment. Okay, so address is also assigned to some data space that has some sizes. Okay, and then this address number 1 is assigned to the 8-bit data. So 8-bit means the byte. Okay. So that means if the address 0 is assigned, this address 0 is assigned for pin number 0 to pin number 7. It's a 1 byte. Okay. And then next bit, like 8 to 15, the address number 1 is assigned. So it's also the size is 1 byte. So address number is assigned to each byte. That is called the byte addressed. So you need to remember that in the computer system, the address is a byte addressed. So it's a byte address. So each byte, for each byte, address number is assigned. Okay, so that means if we see the address number, then that means the address of the variable, then we can find that the location of this data inside of main memory, right? We know the size of this address 1, so we know the address number. Then we figure out the location of this data, the size of the data here. So memory is a byte address too, so you need to remember that. And then RISC-V is reader endian. So endian means the how data is assigned inside of main memory. Then I will explain using this slide. So actually the size of data is larger than byte. So for example, if we use the, so it depends on some computer system, but usually the size of integer data in the C is 4 byte. So 4 byte. So 4 byte means, so 4 byte means that it's larger than 1 byte. Then how can we assign this 4 byte data in the main memory? So this is the example. So this is the 32-bit integer data. That means it's a 4 byte. And then we declare the variable A. It has this number, so it's a hexadecimal number. Then how can we assign this variable A into main memory? So there are two different mechanisms. So reader endian means that, so A has the 32-bit integer from pin number 31 to pin number 0. So reader endian means that the smaller number part is assigned to the smaller address number. It's called the reader endian. Okay. Sorry, my writing is not good. So in the reader endian system, it's called the RISC-V part. So if you took this is the logic design. RISC-V means the bin number is smaller, and then MSV means the bin number is larger. Okay, so this RISC-V part, the first 1 byte RISC-V part is stored in the smaller address part, smaller memory space that has the smaller address number. Okay, address A. And then the next byte is stored in the A plus 1 because it's a 1 byte. And then the next byte is stored in the A plus 2. This is the little endian scheme. The big endian is the opposite. MSB, that means that the bin number is large, that because 32 to 24 is the first 1 byte is stored in the memory space that has the smallest address here. And then the next byte is stored in the A plus 1. The next byte is stored in the A plus 2. This is big endian system. But you need to remember that RISC-V processor use the reader endian system. Okay, so that means if the bin number is small, this byte is assigned to the byte space that has the small address number. So it's a little endian system. And the big endian is different. So if we use the little, so actually the little endian is a more natural. It's called, how can you say, it's more natural than the big endian system usually. And then most of computer systems use reader endian system. Okay. And the RISC-V is a reader endian. And then another feature of RISC-V is that RISC-V does not require words to be aligned in memory. So words means that, so usually the words means the size of data or the memory chunk accessed by accessed in one cycle. So there are two different meaning for words, but we sometimes use words for the some size of data, like the byte. Usually words means the 4 byte. Okay, but sometimes we use the words for the size of data accessed by one clock. Okay, so there are two different meanings, but you can RISC-V does not require words to be aligned in memory. So that means so usually the word is the 4 byte, so it's a 32 bit, and then for normal processors, so because the size of a word is the 4 byte, so the address of this word should have multiple of 4. Okay, because the size of word is 4 byte, and then we already learned that the address number 1 means the byte. Okay, so normal processor, for the normal processor, the address of a word should be multiple of 4. So 사의 배수, multiple of 4. But in the RISC-V, this word is not aligned. So usually aligned, but we don't need to align words in the multiple of 4. So that means, so this is the memory space 0, 1, 2, 3, and then memory space. This is the address 4, 5, 6, 7. So aligned means that this is the word. If the data has one word size, then this data should has the address of 0 and address of 4. So that means that the word is aligned in the main memory. But in the RISC-V, we don't need to align this word data inside of the memory. So that means that if the word has the address, so a word can have address 1. So that means that this word occupies the memory space from 1 to 4. Okay, because the word address is 1. So word address just point the start byte address in the main memory. Okay, so RISC-V supports this data assignment. Okay. Okay. Okay, so let's see the example of memory operands. So this is the example code of C code of the C program. Then you can find that this is the array data A, and then the A12 is equal to variable H plus A8. So how can we translate this C code into RISC-V assembly instructions? So this is the array data, and then so array data means that the multiple element can be stored in this memory spaces. So this is the memory space, and then A0 is assigned to this space using some address, and then that means that A1 is assigned to the next space, and then A2 is assigned to the next memory space. This is how array data is assigned in the main memory. And then in this example, the H is stored in the register X21 and then base address. So what is the base address? So base address means the address of A0. So that is the base address of A means that this is address of A0. So in order to represent the address of a variable A, we frequently use the operator AND. Okay. So if I use the A, so that means that this is the address of A0. Okay. So base address of A is the and then we assume that the size of a single element of A is 8 byte. That means the size of this single element of A is the 64 bit. That means it's called the double word. Got it? Then how can we translate this code into RISC-V assembly code? So in this example, the H is already in register X21. So we don't need to transfer this data to register file. Okay. But the data is stored in the A8, and then this A8 is in the main memory. So how can we transfer this data to the register file? And then we already know that base address of A. So that means that the address of A0 is stored in the register file X22. So the first, because this data of A8 is stored in the main memory, we first transfer this data into register file, because RISC-V instructions can access, not except the memory instruction. So RISC-V instructions can only access data in register file, except memory instructions. So first we need to transfer data in A8 into register file. So how? So we first need to know the address of A8. You know the address of A8. How can we calculate the address, this address? So we know the index of the A8, the index is 8, and then we also know the size of a single element of array A, that is 8 byte. And then I already explained that if array is declared, the array is assigned to the memory like this. So the next element of array is assigned to the next memory space of main memory. Okay. Then we can, if we know the address of this A0, then we can easily calculate the address of A8. So that is address of A8 equal address of A0 plus what? 64, because it's 8. Okay. So this is the base address of A, and then this is the offset. So that means that this means the X22 plus 64. Okay. So with this offset and the base address, we can calculate the address of A8. So this is the load X9, 64, X22. That's it. So that means this load instruction means that calculate the address with the x22 plus with this offset 64, and then transfer data inside of the memory space that has the address of x22 plus 64 to x9, the register x9. So this data in A8 is stored in the x9. Oh, x21 is here. H is in x21, and then we transfer data to x9, and then we can calculate the H plus A8. Okay, here, right? And then also the result is stored in the x9. It's possible. So just to read the data from the x9 and then store the result to the x9 also. So x9 is updated to the H plus A8. And then this C code represents that the result is stored in the A12. So A12. It's easy. Also, in order to store the data inside of a register to the main memory, we need to use the store instruction. So SD means the store double word, because the data size is double word. So this store instruction read the data from the register number x9 and then store this data to the main memory that has the address of x22 plus 96. It's the same format. So that is the address of A12, because, understand? You see? Okay, understand? So I don't know whether students understood this slide, because I was not able to see student's face. Okay, let's move on. So register versus memory. So I already explained the register is a small temporary memory space, and then usually we call main memory is just a memory, because this is some real memory inside of the computer system. So if we say that, oh, my computer has 8 GB of memory, so that means that the main memory size is 8 GB. Okay, so this slide just compares the registers and memory. And then I already explained the register is very small, the size of the register is very small and fast. Then size of the memory is very large compared to the register file, and it's very, very slow. And then in order to use data inside of a memory, then this data should be transferred to the register file, and we need to use the instruction, load instruction. Like, so I frequently use the load like LD, but actually this is load. And then in the RISC-V processor, there are 4 different types of load instruction, but these 4 different type of load instruction just to specify the size of the data. So if the data size is byte, then we use the LB, B means the byte, and then if the data size is half word is 2 byte, is we use the LH, and then LW is the data size is a word equal 4 byte, and then LD is the double word. Data size is 8 byte. Okay, there are four different rows in the RISC-V, and also store is the same. There are 4 kinds of store instructions like SV, SH, SW, SD. Okay. So, okay. Also, in order to transfer data from register to the main memory, we need to use the store instruction. And then in the RISC-V processor, there are only 2 kinds of data transfer instruction, like load and store instructions. And then all other instructions just access data inside of a register file because it's very fast. Okay. But we already know that the number of registers is also limited. So there are only 32 general purpose registers in the RISC-V processor. So this is a very precious resource. So compiler needs to maximize the utilization of this register file. So compile, actually the high level program is called the compile. High level program is compiled into assembly code, then the compiler assigns the register number to the translated instructions. So compiler need to manage these precious general purpose registers because the register number is limited. Okay. Register optimization is so important, but it's a job of a compiler, not computer architect. Okay. And then we can use also immediate operands. So until now, we learned about the operands from registers, and then operands from memory, and then the third type of operands is immediate value. It's immediate value. So immediate value means it's just a constant number. I frequently use the number as the sharp letter. So it's a immediate value is just constant number, but the size of this number is small. Also, the RISC-V processor supports the immediate operands like add, I. So what is the difference? So this is the example of immediate operands of addition. So what is the difference? We already learned that arithmetic instruction like add x1, x2, x3. And then this is the immediate add I. So x22, x22, and 4. This is just a constant. So what is the difference? Add means x1 equal x2 plus x3. Right. So this add instruction, normal add instruction, reads data from the register files x2 and x3 and then store result to the x1. So this is add I. So that means, so this is the destination register. So this means x22 equal x22 plus 4. So in the immediate instructions, this instruction just use the constant value directly. So why this immediate instruction is included in this RISC-V ISA? Because it's useful. So in the normal application or normal program, we frequently use the very small constant number. So for example, we frequently use the for loop like for I equals 0, I is less than 100, and I equal I plus 1. So this is the for loop. So where is a constant? Here. We increment the variable I by 1 for each iteration. So 1 is the very small constant number. So actually in our normal program, these very small constant numbers are frequently used. But if there is no immediate instructions, then we need to write the code like A equal 1 and then B equal C equal A plus B, sorry. A equal 1, B equals 1000, and then C equal P plus A. So in order to write this code, we firstly assign a memory space for A in the main memory, and then transfer data to the register file like X1, and then also assign the memory space for B, and then transfer this data to the register X2, and then calculate the add X3, X1, X2, and then store X3 to memory space for variable C. But this A is very small number. A has a very small number. So instead of assign the data space for variable A, because this is a very small number, we can directly use this constant like add X3, X2, 1 like this, or add I because it's an immediate add. So what's the benefit? What's the advantage? We don't need to assign memory space for A, and then we don't need to use load instruction. We don't need to use this load instruction. Then we can save the number of instructions. It's very important. Why? Because the computer, so we learned about the performance of the computer system. The execution time is instruction count, CPI, and clock period, right? If we can reduce number of instructions, we can reduce execution time, then we can increase the performance of this software, this application. That means the performance of computer systems, right? So it's very, it's very important to reduce the number of instructions. Okay, and then if we use this immediate operands or immediate type instructions, then we can reduce the number of required instructions because we don't need to assign the memory space, and then we don't need to use load instruction, and then the small constant number is directly included in the instruction and then directly used. So by doing this, we can reduce the number of instructions and we can increase the performance. It is possible because we frequently, it's very important. We frequently use small numbers in program. Cool. So that means small constants are common, and then make common case fast. We add immediate instructions. Okay. So that's a benefit of the immediate instruction. So RISC-V also supports the immediate instructions for arithmetic instruction, or we will learn about other logical instruction. So if RISC-V also supports the immediate instructions. Okay. So the third type of operand is immediate value. And then in order to use the immediate value, we need to use the immediate instructions that has I postfix. Okay. Okay, so understand? Okay, we learned about the three types of instructions, three types of operands. First, the register type, the second, memory type, and third, immediate type. Okay, there are three types of operands in the RISC-V instructions. Okay, now let's learn about the signed and unsigned number. But I think it's basic, so it was actually this number system is already covered by the prerequisite course, the digital logic design course. So I briefly explain about this number system. So signed and unsigned number. So we already know about the binary number, and then each digit of the binary number has the value of power of 2, and then it's the same to the decimal number. So it's some decimal number. So if this is the decimal number, then this means the 10 to 0, it's a 10 to 1, it's a 10 to 2, this digit. And then it's same to the binary number. Each digit represents the power of 2. Okay, and the same. And then what is the unsigned number? Unsigned. So unsigned means that it's just a positive number. So each digit is all digits of these binary numbers are positive. So unsigned number is represented like this, and then also we can know the range of the n-bit number is 0 to 2 to n minus 1, because all zeros are 0, and then all ones are is 2 to n minus 1, right? And what is signed integer? In the signed integer, the MSB means signed bit. So that means if the MSB is 1, that means it's a negative number. And then actually in the 2's complement signed integer, if the MSB bit is 1, that means it's minus MSB bit multiplied by 2 to n minus L. So what is different? In the unsigned number, there is no sign, minus sign here. Okay, so it's a MSB bit multiplied by 2 to n minus 1. But if we use the signed number, signed integer, then MSB means the minus sign. Okay, so and then we already know that the MSB bit has the largest magnitude. So if the MSB bit is minus sign, then that means the other digit minus the MSB bit multiplied by 2 to n minus 1. So because of this feature, the range of signed integer is the minus 2 to n minus 1. That is the 1, 0, 0, 0, 0, and then 2 to n minus 1 minus here minus 1. Okay, that means 0, 1, 1, 1, 1, 1. So the largest number of the 2's complement signed integer is 0, 1, 1, 1, 1, 1, 1, and then the smallest, that is the smallest number is the 1, 0, 0, 0, 0, 0. So it's a signed number, right? So it's just a review of the digital logic design. So and then RISC-V has the fixed bit width for the registers for each general purpose register. So actually we use, for this course, we usually use the 64-bit data. That's the double word data. And then like add x1, x2, x3. So that means that we use this instruction use the data inside of the general purpose register, and then the size of the register is 64-bit. That means the width of the register. And then we just use the integer data. That means the 64-bit integer data stored in this register file. Okay. So if we handle the signed number, the MSB bit is the signed bit. And then if the MSB bit is 1, that means the negative number. And then, but if we just use the unsigned number, MSB bit also represent the magnitude of the positive number. So that is just positive, okay? Positive numbers, okay? And then I believe most of the students know how to negate the numbers, okay? It's just to change the sign of the number, like A equal minus B. So how can we negate the a certain number? It's just the inverse of all digits plus 1. That is the minus x, right? So it's a basic of the two's complement number, okay? So it's just to review. And then, it's somewhat, so you need to remember how to extend the sign bit, actually. So sometimes the instructions handle unsigned number, and then sometimes instructions handle signed number. So, and then usually the size of data can be different. So sometimes we handle the byte data, and then sometimes we handle double word data. Like it's a 1 byte, and then size of the double word is 8 byte. And then sometimes we use the 2 different data which have different size. Okay. Then what should we remember? So if the size of the data is different, then we need to extend the size of the data that has the small number of bits. Okay. So let us assume that A is the byte data, and then B is the word. The size of the B is the word, and then C equal, so it's the word A plus B. Because the size of A is different from the size of the B, then we need to extend the size of variable A for this equation, or this instruction. So in that case, we need to extend the size of A. Then how? We need to consider the signed number or unsigned number for this A, variable A. So if A is unsigned number, for this extension, we just need to add zeros in the MSB of A, right? Just to add 0. The magnitude is the same. But if the A is a signed number, then we need to consider the sign bit of A. So if the A is the signed number, and then if the MSB is 0, we just need to add zeros. And if the sign bit is 1, then we need to add ones, right? So if that means if the A is the signed number for this extension, bit extension, we just repeat the MSB bit. Okay, so that means for this extension, bit extension, then we need to consider the data is signed number or unsigned number. Okay, so that's why I explained this. It's obvious. RISC-V also supports some special instructions for this bit extension. For example, this is the load byte. The load byte means that just read byte data from memory and then transport this read data to the register file. But we already know that, so we are learning RV64I. So that means the size of register is 64 bits. But this load instruction just transfer byte data. The size of byte is smaller than the 64 bit. Then how can we extend this bit number of byte data? So there are two types of load byte instruction. So if we use the just LB, then we think that this byte data is signed data. So this 8-bit data is transferred to the register file, and then the bit is extended, but we apply sign extension. Okay, so that means the MSB bit is just repeated and then filled in the target register. But if we use LBU, that means U means the unsigned. So LBU, then we apply 0 extension to the MSB of the transfer data. Okay. So based on the signed data or unsigned data, then we may use the different instructions like LB or LBU. Okay. 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 And then let's see how our assembly instructions are translated into machine instructions. Okay, this is another topic. So the next topic is representing instructions in the computer. So that means that representing instructions in binary data. So until now, we learned the instruction of the RISC-V like add x1, x2, and x3. So this is the assembly instruction of RISC-V, but we can, so if we see this instruction, then we can understand what instruction means. So it's add, so that means it's x1 equal x2 plus x3. Also, we already repeatedly learned that, oh, this means that read data from the registers x2 and x3, and then compute the x2 plus x3, and then store the result to the target register file. Okay, but a computer is a digital system, so computer processor cannot understand this instruction because this is not a binary data. So actually this data, this assembly instruction need to be translated into machine code. So that means binary data. So this instruction need to be translated into the multiple bits and each bit has the 1 and 0, 1 0 0 right, 1, something like that. So because a computer only can understand bit data, like 1 and 0. And then let's see how the assembly instructions are translated into binary data. Okay. So this translation rule is also defined in the instruction set architecture manual. And then this translation is called the decoding. So it's a instruction decoding, because this assembly instruction are actually the one-to-one map to the binary code, that is the machine code. And then this rule is defined, and then in the ISA manual, so this rule is also defined. So, and then we also need to consider the complexity of decoding hardware. Okay, so that means so actually, so this add instruction, so add instruction can be translated into multiple bits, like 1 0 0 0 blah 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 blah. Then these bits are given to the computer processor, and then computer processor, if computer processor receives instruction that is the machine code, then computer processor needs to decode this instruction. That means that a processor needs to figure out what kind of instruction is received. Okay, that is called the decoding. And then the component that decodes the instruction is called the decoder. And then in order to simplify the structure of a decoder, then we need to also apply the regular rules for this instruction translation. Okay, that so we can represent the instructions into some binary data, and then if we use just the binary data, then the length of the instruction can be very long. So we frequently use the hexadecimal number for this course. Okay, and then the RISC-V has the basic formats for this instruction translation. So this slide shows the 4 types of instructions in RISC-V, four different formats of instructions, like R type, I type, S type, and U type. So what does that mean? So if you see these instruction formats, then you can find that these are bin numbers, like 31 to 0. So the size of RISC-V instruction is 32 bits. So this number represents the bin number of an instruction. The bin number 31 to bin number 0. And then each instruction, X1, X2, RD, RS1, RS2. So these instructions has its own format. So actually the add instruction is the R format instruction. And then these instructions are decoded into binary machine code based on these instruction formats. So this slide shows the 4 different instruction formats of RISC-V, and then you can find the formats here in the reference card. So format here. Or add is the R format, and the add immediate, like add I is the I format. Okay. Then also you can find, French is the P format. What? And then there is no load or store instructions here. Okay. Okay. So this is the add instruction, and then we already learned that add is the R format instruction. So that means each instruction of the add is add instruction, and operands of the add instruction like RD, RS1, RS1 and RS2 are assigned to each field of instruction. So for example, for add is the R format. So add RD, RS1, RS2. So if we see this instruction, we can find 4 different information. So what does that mean? This is the add. This is add instruction. This is the target register. This is the source register 1. This is the source, source register 2. So there are 4 different information in this add instruction. And then we can assign each instruction to each field of R-type format instruction. So if you see that this R-type format, you can find that, RD is here. This is RD. RS1 is here. RS1. RS2 is here. And then you can find that 5 bits are assigned to RD, and 5 bits are assigned to RS1, 5 bits are assigned to RS2. Why 5 bits? Because the number of registers is 32. Okay, so that's why each register has 5 bits length. So for example, if RD is 0, 0, 0, 0, 1, that means that it's X1. Then 0, 0, 0, 0, 1 is filled in this RD field of R-type instruction. So we can assign the register numbers to the RD, RS1, RS2. Then we can assign the information of add to the using function 7, function 3, and OP code field. Okay. So using these bits, we can represent the add instruction. This is the R type. And then I type, like, 1 minute, just 1 minute. We add I, RD, RS, and immediate value. So then we need the bit field for this immediate value. So for the I type instruction, RD is here, it's the same. RS1 is here because RS1 is here. Then immediate value is assigned to the 31 to 20 here. Okay. So immediate value has only 12 bits because immediate value, I already explained that immediate value is the small constant number. So we just need the 12-bit number. Okay. So immediate value is assigned to this field. And then OP code and function 3 is used for representing add. That's it. So this decoding rule is also defined in the RISC-V instruction set manual. So, and then I also show the example of decoding. And the next class, we will learn how the instructions are translated and then decoded into the machine code. Okay, and I think I already explained most of the decoding rule of the RISC-V. Okay. Thank you for your attention. Do you have any questions? So, okay. Okay. Thank you for listening, and then see you in the next class. And if you have any question, post your question on the Piazza. And then also you can ask a question after this class. Okay. Thank you and bye.